So now we are ready to talk about vector surface integrals. So I definitely want to set up what we're going to do from what we've done in the one-dimensional graph case in order to prepare us for what we're going to do right now. So previously, we considered what it means to integrate a vector field F over a one-dimensional curve C, which is described with a one-variable parametric equation R. So it worked out like this. The line integral over the curve f dot dr, written out, parameterized, look like this. The integral from between your boundary values t1 and t2 was your vector field f, now function of t, dot vector dr dt, all of that dt. So remember, that was that big step. So now we're going to talk about what that means in the two-dimensional case. So to integrate a vector field f over a two-dimensional surface S described with a two-variable parametric equation R. Okay. So before we actually start doing the vector surface integrals themselves, we need to take a moment to talk about orientation. So let's do that. Okay. So what did orientation used to mean? So for a one-dimensional curve, remember that the line integral, the integral over the curve of f dot dr, could also be written as the integral over the curve of vector field f dot unit tangent vector t ds. And either way you write it, that provided the part of the flow of f, vector field f, along the curve. That's what that dot product did. Now we also briefly calculated the flux line integral, and that was the integral over the curve of f dot n ds, where n is the unit normal vector. And that provided the part of the flow of f across the curve. And then further, for each line integral, we need to specify which direction we intended. So there are two choices with a curve with endpoints. There are two choices forward. You can think of them as forwards and backwards. And then changing that choice changes the orientation of the curve, and then also changes the sign of the result. So that's all the stuff that we did before. So now what? So now we'll try to do the same thing with a vector field for a two-dimensional surface in 3 coordinates. So here's a big change. So first of all, what is tangent to a surface? We know it's got a tangent plane. Now you cannot describe a tangent plane with, or you cannot describe the direction of the tangent plane with a vector pointing, quote unquote, in the direction of the plane. It doesn't make sense. We know it takes 2 vectors. Therefore, we are not going to talk about vector flow or vector field related flow along a surface, because that would not make any sense. However, perpendicular to the surface is a line, and that, yes, you can describe with a vector. So while we cannot continue to find the flow of f along a surface, we can still find the flow of f across the surface, and we'll continue to call that the flux. Now, once again, in order to do this, we need to choose a positive orientation. And when you're in 3-dimensional space and you've got a 2-dimensional surface, there are 2 ways to cross it. Again, you can think of them as like forwards and backwards. So, okay. So we can indicate each of these directions with a normal vector. Now we already know how to make a normal vector. If our parameters are u and v, it's just we take dr du and dr dv, which are tangent vectors, take the cross product, that gives us a normal vector. Great. And in fact, we're going to take that as our positive orientation, the direction of this normal vector. Now, for our calculations, sometimes we're going to want the normal vector that we'll want the direction, but we do not want to contribute any magnitude. And when you want just a direction with no magnitude, you take the vector and you divide it by its magnitude in order to give you a unit vector, which is like a direction vector. And that we call big N. So there you go. So we are now going to use sometimes the unit normal vector big N. And super important, as you do your calculations, remember to mentally distinguish between little n and big N. Little n is your sort of standardly constructed normal vector, but it's got a magnitude. Big N is the unit normal vector, and its magnitude is neutral, is 1. Okay. So when we calculate unit normal n this way, this is called the positive orientation. And so therefore, we say negative n is the negative orientation. So let's see just how orientation works. Let's do an example. So let's calculate big N, the unit normal vector, for the sphere radius r. So let's see how just calculating the unit normal vector, let's see how that works. So we're going to start with the parametric formula for the sphere, which we can get that by borrowing from spherical coordinates. So the typical spherical coordinates to describe a sphere looks like this, but of course the radius is fixed, so it's just the constant big R. Okay, so now let's calculate it. So we need the two tangent vectors. So drd phi is the first thing, drd theta is the second thing. I'll just calculate the two derivatives, and now we need to take the cross product. So taking the cross, calculate, and you get this normal vector. So r squared sine squared phi cos theta, comma, r squared sine squared phi sine theta, comma, r squared sine phi cos phi. Okay. Now, of course, that's just the normal vector. We're trying to make the unit normal vector. So we need to find the magnitude of this. So the magnitude of it, if you calculate it, things wind up simple. I'm going through the calculations very quickly, but things wind up simplifying. You get like sine squared plus cos squared here and there. So things will combine and simplify, and all it works out to be that the magnitude is r squared sine phi. So you take the normal vector and divide by its magnitude, which is that. So dividing through in each component by that amount, and you get sine phi cos theta, sine phi sine theta, cos phi. And that is the unit normal vector for a sphere. Now, if you're also very clever, you can recognize that that actually bears a very close relation to just the description of the sphere itself. So going back to the parametric equation for a sphere, it's this. And you notice that this is really just the position vector little r divided by the radius. And of course, that makes sense if you visually think about what's going on with the sphere. What's going on with the sphere is that at every point, if you draw a vector from the origin to the sphere, that will in fact be normal to the surface. So it makes sense that the position vector is pointing in the direction of our normal vector, and then here we're just making it into a unit vector. Okay. So one small comment, which will be relevant for us when we use spherical coordinates. So far, it didn't matter if we do r cross u or r cross v or rv cross ru. With spherical coordinates, we will specifically want to do r phi cross r theta, not the other way around, in order to get the orientation that we are familiar with. In order to get, the typical orientation. What's the typical orientation? The following, for a sphere, is the following thing. As we just calculated and discussed, Our normal vector, either little n or big N, will point outward at every point on a sphere. So the sphere is an example of what we call a closed surface. A closed surface is a surface, which remember is two-dimensional for us, which is the boundary of a three-dimensional solid. Now, it is always true that normal vector n will point outward at every point on any closed surface. And then typically for a closed surface, we will take the outward orientation. Also, another type of surface we deal with quite a lot, our special case, a surface which is described by the function z equals f of xy. So that kind of surface everywhere has a top side and a bottom side. And in that case, typically we will take the upward orientation. And we also know how to find the normal vector by a shortcut for that one as well. And just a quick note about terminology. Saying orientation or positive orientation or normal direction, that all means the same thing. Okay. So there's one fun point about orientation. It turns out that not every surface has an orientation. Doesn't seem right. It seems like a normal vector is always something you can calculate, so it shouldn't be a problem. Well, I want to give you an example, and this is an example that you can actually build this surface for yourself. Okay. So the simplest example of a surface that does not have an orientation is something called a Mobius strip. So you can make your own Mobius strip if you take a thin strip of paper, as illustrated in the diagram on the left, curl it into a circle, but give one end a half twist before attaching the ends. And that's illustrated on the right. So now a crazy thing happens, which I'd have to demonstrate in person, maybe for you to believe it. But you can make a Mobius strip for yourself. Make a strip of paper, tape the ends, and then you can do the following thing. Take a pencil and start drawing a line in one direction. You'll wind up on the opposite side from where you started. And then if you keep going, you'll continue to, again, without picking up the pencil, you keep going, you'll wrap all the way around and connect back to where you started, but there will be a line on what you thought were both sides of the sheet. Therefore, this piece of paper only has one side. It's a crazy thing. It's actually a lot of fun to do yourself, and I recommend that you try it. So, and as one corollary of this, which is when you draw, or when you bring your pencil around, you can come back to the exact same point where you started, but you're on, can't say the other side, but you'll be at that point and your pencil will be pointing in the exact opposite direction of where it was originally. And that's, again, without picking up the pencil. So what that means is that you can move your pencil, which is your normal vector, continuously around the surface and have it point in be at the same point and point in the opposite direction, which means that that surface can't tell the difference between forwards and backwards, between the two directions. Therefore, it has no orientation. Note that you could never do this on a sphere. You can't start with a pencil or a normal vector at one point pointing in one direction, slide it around, and somehow magically end up on the other side. You'll always be on the quote-unquote outside of the sphere. So a surface like that is called an oriented surface. So moving your normal vector continuously around the surface never results in normal vectors in opposite directions at the same points. A surface like this Mobius strip is called a non-oriented surface. You can move your normal vector around continuously, and you can get normal vector in opposite directions at the same point. Okay. So I just wanted to mention that surfaces without an orientation do exist. We're not actually going to do anything with it, except that I, again, suggest, and I would love for you to try that at home because it's actually really cool. Okay. All right. And then one other quick comment. We've talked about orientation with two-dimensional objects, and now or in two coordinate dimensions, and now we've talked a little bit about it in 3 coordinate dimensions. How does this all work in higher coordinate dimensions? Starts to be more complicated. And doing integrals with different dimensional things in higher dimensions is also more complicated. That's all I want to say about that. Okay. So that was a quick word on orientation. So now that we've got this idea, so basically we know we're going to use our normal vector, and if we ever want to discuss direction without magnitude, we know we need to make it a unit normal vector. Okay. So knowing that, we can now start talking about how do we make a vector surface integral. And as a reminder, our vector surface integral is going to involve a dot n, so it's really about what's happening across the surface. So for that reason, it's often just called a flux integral. Okay, so how do we write this down? So first, as a reminder where this comes from, remember that we did have a flux line integral. So previously, we calculated the flux of vector field F across a one-dimensional curve C with what we call the flux line integral, the integral over the curve C of vector field F dot unit normal n ds. Now we calculate the flux of vector field F across a two-dimensional surface S in 3 coordinates. So how do we update these things? So we're going to say that we know that F is a continuous vector field, and now S is going to be an oriented surface. So it's the surface regular S, but it's going to be oriented with unit normal vector big N. So now we have the definition. The vector surface integral of vector field F across oriented surface S is this: the double integral over S of F dot big N ds. And another thing is that one thing we do is we define d bold S, or oriented surface, as unit vector n ds. So using that notation, we can write the integral as the double integral over the surface of F dot ds. And this, like I said, this integral is also called the flux of vector field F across oriented surface S. And this last thing, being able to write it as F dot ds, I suppose you could say it's not necessary, but it is nice because it actually looks a lot like, now it looks like our line integral formula, which was F dot dr. So this is how we represent the same thing. Okay. So one more thing. So when we do these integrals, we need to know how to take so this is the original statement of what is a flux line integral. Here's the definition. Then we will need to calculate it. So as we've seen before, the first thing you need to do is you need to start moving it to writing it parametrically. So how do we do that? Well, we know that, so the double integral over the surface of F dot ds, by our definition, is just the double integral over the surface of F dot n ds. But we know what ds is. We know what d regular S is. We know that is the magnitude of n dA. And we also know that unit normal vector is the normal vector divided by its magnitude. Well, look what we have. We've got divided by magnitude of n times magnitude of n. That stuff cancels, and you get the integral over the region where now we're in now we're talking, everything is expressed in parameters of vector field F dot normal vector n, little n, dA. And so this provides us with a transformation rule for how we can write, for how we can calculate our flux integrals. We know that d of bold S is just normal vector n dA, and we know how to calculate normal vector n. And as a note, in a sense, we already were doing this because we knew that ds, d not bold s before converted as the magnitude of n dA. And basically now we're writing everything not just with magnitudes, but basically as a vector with the orientation, blah, blah. So let me also mention, we won't go through it in great detail, that this double integral can also be constructed through approximation. So I will just mention that here and you can consider it for yourself. Okay. So now let's get directly into an example. So let us find the vector surface integral, which we can also say is just the flux, for this vector field 0, 0, z across the surface S, the sphere centered at the origin radius a, unit normal pointing outward, which is basically the typical orientation. Okay, so how do we do this? So the first thing we're going to need is we're going to need a parameterization. So we know that the sphere can be parameterized. So we're going to borrow our parameterization, as always, from spherical coordinates. So normally there would be three variables that we use to parameterize a sphere, but we know our sphere has a radius a. So so the radius part just becomes a constant, and then the formula for this sphere becomes r of phi theta equals a sine phi cos theta, comma a sine phi sine theta, comma a cos phi. And then with the usual bounds, we know that phi goes from 0 to pi, and theta goes from 0 to 2 pi. Okay. Now, we kind of already constructed the unit normal, but let's just go through it again really quickly just for practice. So we know that we know how to construct the normal vector. We just find the two tangent vectors and take the cross product. So in this case, we're not using u and v. We will use phi and theta because that's what we're used to for spherical coordinates. So r phi is a cos phi cos theta, a cos phi sine theta, negative a sine phi. And then r theta is negative a sine phi, sine theta, a sine phi cos theta, and 0. Now we take the cross product. And taking the cross product, you get a squared sine squared phi cos theta, comma a squared sine squared phi sine theta, comma a squared sine phi cos phi. So there's your normal vector, written in phi and theta. And now we'll have to write the vector field parametrically as well. That's very easy. It was just 0, 0, z. So now it's 0, 0, and z is a cos phi. So that's everything we need. We've now written everything parametrically. We can now write down the integral. So the integral written generally, the flux integral written generally is just the double integral over the surface of vector field F dot unit normal n ds. And this converts as we just saw, into the double integral over the region of vector field F dot normal vector little n dA. So, and before I go on, let me point out how important this is. To understand that, to distinguish for yourself big N, which is the unit normal vector, and then little n, which is your your normal vector, but with the necessary magnitude. Okay. So make sure you understand the role of each of those. Okay. So continuing, now we just plug in what we figured out. So we know vector field F is just 0, 0, a cos phi. Here's n, normal vector, which we also calculated. And dA, our two parameters are phi and theta, so it's just d phi d theta. And then with the appropriate bounds. Theta was 0 to 2 pi, and then phi was 0 to pi. And in this case, because the bounds are constant, you can do it in either order. It's no big deal. Okay. So taking the dot product and, taking dot product, two of the components are 0, so that worked out nice. You'll just get a cubed sine phi cos squared phi d phi d theta. So we do have a cos squared phi, so you have to use the, you have to do a substitution. So we'll take u to be cos phi, and then du will be negative sine phi d phi. And then after making that substitution, doing the integral, you get negative 1/3 cos cubed phi, phi evaluated from 0 to pi. And a cubed is the constant, so that pulls out. And so from that, you get 2/3, and 2/3 also a constant, so that just pulls out. And I get the integral from 0 to 2 pi of d theta. That's just theta from 0 to 2 pi, so it's just 2 pi. So combine the constants, and you get 4 pi a cubed over 3. So there's our first example of calculating a vector surface integral, also called a flux integral. Let's do another example. And for our second example, let's do our other example here. So calculate the flux of this vector field F equals xy, comma yz, comma zx across this surface. So z equals 4 minus x squared minus y squared, with x goes from 0 to 1, y goes from 0 to 1, taking the upward orientation. Okay. So how do we do this problem? So the main thing is to note that this surface is written with z as a function of xy. And we know that's a special case, which gives us some nice shortcuts. So we know that the normal vector, little n, is just going to be negative fx, comma negative fy, comma 1. And we can calculate that real quick. So that is 2x, comma 2y, comma 1. That is our normal vector. And also we know that we can just use x and y as our parameters. So we'll just continue to do everything in terms of x and y. So then we can rewrite, so then you do have to rewrite the vector field because we need to replace z. So the vector field becomes xy, comma, y times 4 minus x squared minus y squared, comma, 4 minus x squared minus y squared times x. And so now everything is expressed in our quote unquote parameters, which are just x and y. And now we can set up our flux integral. So the flux is always the double integral of the surface of f dot unit normal big N ds, which is equal to the double integral over the region, meaning in terms of our parameters, of vector field f dot normal little n dA. And now we plug stuff in, and here I've already taken the dot product. So 2x, 2y, comma 1, sorry, other way around. F is, vector field F is right here, dot your normal vector, which is right here. And then, so that gets calculated. That needs to be simplified, of course, but then also we know that dA just becomes, in this case, I wrote it as dy dx. Both are going from 0 to 1, and the order of integration will not matter for something this simple. Okay. So doing a bunch of algebra to simplify that whole expression, you get 2x squared y plus 8y squared minus 2x squared y squared minus 2y to the fourth plus 4x minus 4x cubed minus xy squared. So a long thing, but it's just a polynomial. And now we do the integral, integrate with respect to y, and then evaluate from 0 to 1. Then integrate with respect to x, evaluate from 0 to 1. Doing it really quickly, it's straightforward, if perhaps a bit tedious, but you wind up with 713 divided by 180. And so that is how you do calculate a flux integral. We did a couple of examples. The first example was where we do have some kind of parameterization. We used phi and theta, but of course you could have written it using u and v. And in the second case, we have our shortcut, where since z equals f of x, y, we're just going to continue to use x and y, and those become our parameters.